So, there was a request to go through some more analyses. I think what I'd like to do first is to open this other one first. So here we have a test of Headstart. And one of the things that makes it somewhat interesting is it also shows us an example of potentially correction for attenuation in the model. The outcome is cognition over here, and that has in this model two predictors, the SES level and the Headstart values. They're also, it's kind of interesting to take a look at this part of the model because it's an example of how you can do multiple factors. All four of these, mother's education, father's occupation, and income, this is an old 1978 thing, so these days we would probably do something a little bit different for looking at occupation, were taken to be indicators of SES, plus there was also thought to be some correlation between mother's and father's education that wasn't explained by SES, and also some correlation between father's occupation and income that was not generally represented by SES. We can't, in this model, look at correlations between SES and occupation. That's because that kind of a model is not identified, having only two indicators. We can have correlations between these education and occupation and the Headstart values. And the focal interest of this paper is to look at whether there's an effect for Headstart. So we can run that. And Amos gives you a little message that says, you know what? Not all of the exogenous factors in your model have correlations. Are you sure you don't want to have a correlation here and maybe not a correlation here? Well, in this particular case, you are overriding kind of that default intelligence because you know what you're doing, so you can proceed with that analysis. And now we see the numbers that follow from that. So if you wanted, you can come back in here and take a look at these parameter values. This model does not yet have a correction for attenuation. So the way they published it at the beginning, you really didn't need any of this in the program because you could have just as easily said high school correlates with occupation and high school correlates with SES and high school correlates with father's and parental education. The reason that they had to do this is Bentler and Woodward were using a program called Lisro, which is kind of one of the early structural equation modeling software programs. It still exists and people still use it. But they needed to make that adjustment in this particular case. As we look at the individual models, here's our unstandardized weights, and we can come downstairs and look at our standardized weights. Whoops, I did not request the standardized estimates to be shown. Okay, now we have them. And we can see that we have a 0.18 standardized effect from Headstart on cognition. And kind of a rather substantial standardized coefficient from overall SES on cognition. We can look at our printout. And as you are looking at a printout, it's helpful to always make sure that things are the way you think they are. Verify that your sample size is the sample size. Verify that these are the variables that you think you have in the model. And this is your place where you count your parameter estimates. There are 16 fixed parameters and 21, and we've got 37 parameters in the model. These are the number of variances and covariances and regression weights in the model. And in faith, you might actually skip over the beginning of that and skip directly to the notes for the model. Here is where you want to verify that things are the way you think they are, that we're analyzing the variance covariance matrix. We have 28 degrees of freedom in the data, and our model has 20 parameters. That's going to give us 8 degrees of freedom for the chi-square. And you want to be sure that you've got this, minimum was achieved model that shows that you converged. And here's your chi-square on the probability level. You'll see that later in a moment at the model fit part. And we can come downstairs and look at our fit statistics. Just as before, we can use our wall tests to make a judgment about whether there is an effect from the high school, the Head Start program. And that would be on cognition, this one right here. So based on this, we would say this is not statistically significant. Downstairs, we've got our standardized estimates, and down here are our covariances. There's something interesting that you're going to notice down here with 4 and 5. Notice these two error variances are fixed at 0. Well, one of them is the Head Start program, and the other one, if we're looking at it, E4 and E5 is the income variable. Now, the reason that happened is because in this model, I fixed that to 0. So as there was a request of, what are you going to do if things don't work? Let's just leave that to be free at the moment and rerun the model and see what we get. And if God is in her heaven, you're going to see, hey, there's no answer here. I can't click on this and get any output. This model didn't run. So to have some clues as to why that didn't run, we'll come up here and we'll make it bigger. Down here in the estimates, well, that's interesting. This wasn't supposed to run. It's supposed to be a negative value. Did I free the wrong arrow? B3. That's very interesting. Maybe I'm not getting the right printout. There we go. Is we get a message that the covariance matrix is not positive definite. Well, what's going on there? I got correlations for my latent variables. This is a variance of 1, that's a variance of 1. And all of a sudden, between education and occupation, I have a correlation coefficient of -5. And you have a couple of options there. One was to fix that one variance to 0, which is what Maruyama and McGarvey did. Another one might be to come back and, let's see now which one was the, here we go, education and occupation relationship. Another thing I might do is to come into this sling and consider taking that sling away. And rerunning the model. Well, I'm still not getting an answer. What's going on now? Iteration limit reached. It didn't converge. It will show you the values that you have in here. And 2 things stand out for you. Look at those factor loadings from education and mothers and fathers education. Well, 106 is kind of a large, sorry, 0.16, 0.49 is kind of a large value relative to other things. There might be a local problem. And as you come down here on E2, we see that there's a negative number there. Well, if we come down to the minimization history, we can take a look at what's going on here. So these are the successive approximations for minimizing this value. And the thing that you want to take a look at is this column right here. So the first few iterations, the minimization went down, 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 and was really, really fine. And it's going very, very slowly to a convergence. So if I were doing this for the first time, I might come back and increase the iterations. Amos defaults to only 50 iterations. Well, let's put it up to 5,000 and see if it ever converges. And that takes a little bit. This isn't a large program. Still no happiness. So we'll come back in here and take a look at what's wrong now. It doesn't like it. Iteration limited still exists. And I've got this, oh, I need one more constraint in the model. And if I take a look at my models here, it's going to say, oh, I don't like this at all. I'm not going to run for you. And the minimization history here still is doing the same thing. It's going to go down several thousand, but it's not improving, or it's only improving in the 10,000s place. So, that string of modifications isn't working for us, which is why I originally fit the model that Maruyama McGarvey published, but you had to put in a 0 error variance on that one variable in order for it to run and not have an improper solution. Is that working for you? Is that kind of an example of what you wanted to see of what can go wrong?
I have a question.
Yep.
First, why don't there's no arrow from education to cognition?
That's true. You can do that. They chose not to. And that model would be identified. They did not, generally speaking, the old way that people used to do things was if paths were not significant, they dropped them from the model and then published that. And that's generally, nowadays, we've learned a lot since 1978. That's generally not a good thing to be doing because, first of all, you're to some extent p-hacking, and your model is, given that you peaked and you ran the model first, and you had that in there, you really shouldn't say, oh, I'm going to make my model even better and more parsimonious by dropping it. The second thing is this path from education onto cognition is going to answer the question, is there some unique effect going on? So let me go back to the original model. I don't want to save that. And we'll run that model just to make sure that it runs, is we can easily come in and add that path back in. So I can come into here and put this path from here down to here, and it will default to a free parameter, and I can run that. Oh, that is not running. Okay, well, I'm trying to make modifications on the fly here, but yes, in principle, you would do that. And the second example I wanted to show you is.
Excuse me.
Yeah. Mm-hmm.
Another question about the correction of attenuation.
Yep.
So, what does the model do when does this correction.
Okay, yeah, well,
Is there any different in data in that particular variable after
okay.
the attenuation?
So let's do these things on the fly. And I'm not quite sure if it's all going to work out for us, but let's say that we had some information about the reliability of status and Headstart. Let's say that had some known reliability. You'd have to go out and find a coefficient alpha or an interclass correlation coefficient and put in those values. Now, in this data set, this is an old one. If we take a look at our data, we're working off of the summary data in their data set. You know, they only gave us correlations and they didn't publish the means when they published the papers. This was back in 1978. So what we would then do is, in order, just as an example of correcting for attenuation, we would come down here to this model and we would now fix this variance to be equal to the observed variance of the variable multiplied by 1 minus alpha. Well, this is a correlation coefficient. Let's just say, for example, that we had a value of a coefficient alpha of 0.8. Well, we would then take the variance of that manifest variable times 0.2. Well, since he only gave us correlations, we would fix this value to 0.2 because the variance of HS is 1 times 1 minus alpha. This upstairs here is left as a free value. And we'll hit the run button. And this is our value. So that 0.8 jumped from what it was before. You know, without correcting for attenuation, if we were to come back and do that again, you know, we have 0.18, and originally we had 0.14. You know, correcting for attenuation is also going to increase our correlations with the rest of the factors that we have here. So again, you know, this is an old study. It was published in the Latent Variable Models book. And I thought, well, that would be one example. And I know that it's one of those models where things can go wrong, but that's, you know, an example of how you would set up correcting for attenuation. Notice over here how we identified the model. I have two indicators here. So all I can do in this part of the model is to talk about three elements of the variance covariance matrix. Well, inside of my model, I can freely estimate this error variance and freely estimate that error variance. That's two of them. I get one more free parameter. Well, the only free parameter I can pick is this disturbance. So that means I have to set these two numbers equal to 1. So remember, this is an endogenous factor. And when I have an endogenous factor, I cannot fix this number to 1. It needs to be free because it's an error term. It's the residual variance in cognition after I have adjusted for these other two predictors. If this would have been an exogenous factor, if this wouldn't have been pointed at by anything, I would have some choices. I could either set the variance of cognition to be 1 and estimate one loading between these two, you know, let's just call it L, you know, that would be an equality constraint, and freely estimate these two. That would be a possibility. I could alternately fix that, freely estimate this, and then have the ones here, as you see. And those are, you know, those are your options when it's endogenous. That's the reason I keep mentioning that is in paper projects in the past years, people have forgotten that when your factor is endogenous, you can't get around, you cannot identify the model by fixing that to 1. Anything else? Let's stay with this model, but consider a slightly different program. So this looks identical to what you have before. The thing I want to draw your attention to is this little square over here on the left. And up to this point, we've only had one model in here called default model. And now, when you're looking at that, that has one constraint on it, that V4 is equal to V5. Downstairs here, I'm adding an additional constraint, namely that B2 is equal to 0. And this is an example of doing what I was telling you before. One of the nice features of Amos that the other packages don't do quite so easily, you can start to do this with Lavon now, is it will go in and give you the chi-square difference test automatically in the printout. So as I look at this, I have one model where this is free, and in the second model, it's fixed at 0. So just as we did when we were playing with Onyx, we're saying this model relative to a base model, this model where it's free relative to a base model where it's fixed at 0. And if you look at the printout, you'll get your estimates as before, but what I want to draw your attention to is the model comparison button. And it will then give you the chi-square difference test between the base and the target models. So the difference between these two models is 1 degree of freedom. The chi-square was 1.853, and the p-value is 0.173. How we arrived at that was by looking at the chi-squares here, taking 9.932 minus 8079, 9 minus 8 is 1. So it did that work for you and then calculated the chi-square, and that's kind of nice. It also lets you, inside of Amos, compare and contrast several nested models. So that's kind of a nice feature of that. Right? So is that in the spirit of what can go wrong? And then secondly, here's another model by Maruyama and McGarvey. I use words that correspond to Greek letters just to get you used to seeing Greek notation, because sometimes people use that when they're talking about articles. All of my factor loadings have lambdas, and the paths from latents to latents have gammas. One of the things that we'll talk about later concerns the fact that this diagram is a little unusual in that you're seeing as a path from F4 to F5 and from F5 to F4. This has to do with children's achievement and the achievement of their peers. And that's entirely fine. This is known as a feedback loop. Feedback loops have many concrete things that happen in your life, like thermostats as we get into the fall, where a room gets warm, that triggers a thermostat in the place, and that connects to the air conditioner. The air conditioner comes on and cools the off and on. So that could be the room and the thermostat being that kind of a relationship. When I talk, I'll talk formally about feedback loops later on, but this is just an example of that type of a thing. As we're looking at that model, again, we generate a message here. F1 doesn't correlate with F3, and F2 doesn't correlate with F3. And that was an assumption of their model. And here's our numbers. And here's our standardized values. So these are the two values of our feedback. So, child's achievement tends to cause peer achievement more than peer achievement tends to cause child's achievement values. And here are our correlations. This model, just like the other one, also had to have some fixing going on. By means of an inequality constraint. See, I'm trying to find where it was now. I was prepping this last night. I thought it had a problem with it. I thought it had a negative error variance, but I guess it doesn't. Okay. All right, I guess I must have misremembered. Must be confused with the other one. Haven't had my coffee yet. So, as before, there were choices made about model identification. This is kind of a nice example because we have free factor loadings here and free factor loadings here and a correlation. You might wonder, how come I get to have a free loading here and a free loading here? And in the first example, when it was endogenous, I had to make some choices. Well, the reason that that's the case is this loading is not only doing the work of explaining the correlation between the Ravens and Peabody test, but this number is also estimated by looking at the correlations between this measure and these measures over here. That is, I can go backward here, take this sling and go forward. So, as a result, because this lambda is doing both the work of saying it's an indicator of another variable plus all of the other correlations, I get to freely estimate these numbers here. Just to kind of mess around in real time, if I take this sling away, it's not going to run. So let's come back in here and do that. And hit the run button again. At which point, what? Oh, I'm sorry. I've got to take this one away as well. There, now it doesn't run. And it comes back and says, you need an additional constraint. And downstairs, it says, oh, there's something about Ravens and Peabodys that's not identified in here. And that's kind of the wave as you're looking at the printout to identify where these problems might be. All right. In order, just to open up the box a little bit with arrows that point in both directions, in order for you to identify this model, and there's a former lecture on this coming up, it's the case that you're going to have at least one predictor variable for a factor that's not loading on the other one. So the reason that I can estimate in this model this bidirectional arrow is that this factor and this factor predict F4, but not F5. And in this case, F3 also does not predict F4. And the minimal conditions would be to have at least one. So it's allowed for me to do something like this and this even. Just so long as this thing is not pointing at F4, I should be able to have bidirectional arrows. And I do. So if I'm going to now come back and add this arrow, life should not be happy. And it isn't. You'll need an additional constraint. So, and that constraint could take the form of, well, take away that arrow, or you could take away one of these arrows. So is that working for you? Does that give you some of the guidance you'd like? Everyone's really quiet today. Well, I guess it's a lesson to me to make up a homework assignment over the weekend. Nothing stimulates questions like homework. All right, well, let's come back and take a look at parsimonious models. Last time I had talked about the bifactor model, which has the general form of one great big factor to rule them all and lots of little subfactors. That bifactor model is going to come back and visit us when we talk about multi-trait, multi-method models in a few moments. Hierarchical factor models are also really attractive to people. 9 times out of 10, when I'm talking with people doing their projects, they start out thinking they would like to fit a hierarchical factor model. And I have to admit it's attractive to me as well. And when it works very well. The hierarchical factor model says there are factors that have as their indicators manifest variables. And then on top of that, there's this big superfactor. Now, some things to remember when you're fitting a hierarchical factor model. Just as we talked about before, these factors down here are endogenous because they're being pointed at. So I cannot fix these factor variances to 1. They have to be free. And downstairs, I can identify the model by most commonly setting a loading to 1 and hitting the run button. What sits up here, I mean, and you can also do the eigenvalue decomposition and the little untaught scaling approach and so forth. Any of those really work fine. What sits up here is a factor model which has as indicators 3 latent variables. And 2 things go wrong here when you're consulting with people. One is that they want to specify this large factor, and they also want to have covariances between these factors down here. That's not going to work. And the reason that does not work is because the covariances between these factors are exactly what you're using to get at these estimates of the factor loadings. In other words, this superfactor is trying to explain all of the covariances between the factors by reference to one factor. The second thing that people do is they look up here and they start to think, well, you know, gee, everything's latent up here. I think I don't want to constrain anything. And I'm hoping that as you look at that, you'll say, well, really, in terms of mathematical identification, the rules for how I would identify this factor are exactly the same as those that would happen if these were squares instead of circles. That is, I need to, if I have these 3 indicators, I'm going to have to set something to 1 in order to have the model run. I could set a loading to 1, or if this is exogenous, I can set this factor variance to 1. With 3 indicators, this model is not going to be any more parsimonious than a model that just says there's covariances. Why is that? Well, let's count. I have 3 latent variables. 4 times 3 is 12. Divided by 2 is 6. How many parameters do I have upstairs with the latent variables? Well, 1, 2, 3, 4, 5, 6, and this one was fixed to 1. So this model really isn't going to be anything parsimonious. You can make it part of a larger model and have this predict some other criterion. If you had 4 groups and so forth, then the hierarchical factor model starts to be more parsimonious than an oblique model where you're simply estimating covariances. Any questions? So it's another picture you can draw. In this model, as we're looking at them, then we have our factor loadings here. On our general factor, I picked 3 of the reasons for drinking factors. These are my loadings. Again, as we expected before, conformity does not load well with the other ones, but enhancement and social do, because these two loadings are relatively high. And then downstairs, I have, here's the standardized solution, my factor loadings for the social variables, for the conformity variables, and the enhancement variables, and the error variance is down here. Okay. So before we start talking about the last models in this, it's important to take a breath and summarize. All of the models that we've talked about so far talk about items that load on factors, and they vary in terms of their parsimony. Are these factors simply correlated with other factors, or is there some structure? And that structure can take one of two forms. In things like the orthogonal and oblique factor models, every manifest variable loads on only one factor. In others of them, it's the case that, like the bifactor model, we can see all kinds of loadings on one factor that loads across all manifest variables. And there are these little subclusters that happen. These models vary in terms of their parsimony. The bifactor model, for example, is kind of expensive because it's going to be doing all kinds of loadings. You know, you're going to pay a degree of freedom for each of those factor loadings you have. Other models, like the hierarchical factor model, well, you're explaining all of those relationships upstairs with just 3 of them. So, you know, in terms of AICs and BICs, maybe the hierarchical factor model might show up serving you better. There are other types of models that we'll program that do not show this simple structure model, but actually correspond to a study we're doing. And one of those is the multi-trait, multi-method factor model. This year, I seem to be doing a lot of doctoral comps defenses, and it seems that if you're in clinical, one of the things they want you to talk about is multi-trait, multi-method factor models. So here's an example. This is a study where I've tried to find an example out there of some publicly available data set. And what we have here is a small sample, 174 children, who were evaluated by a diagnostician, the child's parents, as well as the child. So in this situation, this is a little bit of an ugly diagram, but bear with me. I've got anxiety, depression, psychopathy, and generalized anxiety as things that people were asked about. And I have reporters. I have the diagnostician, the parent, and the child. So each report is, this is the diagnostician's report of social anxiety, the parent's report of social anxiety, the child's self-report of social anxiety. And all of those manifest variables are measures of social anxiety. Same song for second, depression, psychoticism, and generalized anxiety. Some of these things, some of these reports are common in that they're all by the diagnostician. So that's why there's a factor loading from here to this one, and here to this one, and here to this one, and here down here to this one. It takes a while to start drawing bendy arrows, but they all go there. Similarly, there's a factor that explores the parent's report and the child's report. So, I took a moment to try to draw each of those loadings for the diagnostician, parent, and child in the model. So when we fit this model, we're going to get loadings on the traits, and we're going to get correlations among the traits. So in this case, here are my loadings from the diagnostician on anxiety disorder, anxiety disorder, anxiety disorder across these 3 reports, psychopathology, generalized anxiety, and I've underlined which things we have here as significant. And downstairs, for each of the manifest variables, I have error variances in the diagram. And in here, I have the method factor loading. So these are the diagnostician's report of each of these pathologies, and the parent reports of each of these, and the child's report of each of these. So at the end of the day, I can then look at correlations between the methods, who's doing the diagnosing, and we find out that, gee, parent and diagnostician tend to correlate relatively highly. They don't seem to correlate very highly with child report. Child report stands by itself. And the correlations between the traits then are adjusted for who's doing the reporting. So I think that psychopathic deviance and schizophrenia have a negative correlation, and generalized anxiety and SAD have an extremely high correlation. So the benefit of this is you're getting correlations among the traits that are not contaminated, or for which the effect of who's doing the reporting has been removed. These correlations then are, in addition to being corrected for attenuation because I'm estimating error variances, are also corrected for who's doing the diagnosing. If I would have just done a study of what's the correlation between diagnostician reports of these psychopathologies, these loadings would be wrong. That is, if all of these circles were gone and I just had diagnostician reports, because the latent variable of systematic bias according to who's doing the diagnosing is not accounted for in the model. Now, you may have noticed that there's no correlation between, say, generalized anxiety and child. Why can't I do a sling there? Well, that model is not identified is the issue. Sometimes multi-trait, multi-method models suffer from identification problems, that they run and run forever and they never converge. And for that reason, some people have said, what I'm going to do is to remove one of the methods, say the diagnostician from the model, and interpret the factor loadings from the parent and the child as relative to a control group of the diagnostician ratings. These models generally go underneath them. More generally, multi-trait, multi-method models go under the nickname of CTCM, correlated trait, correlated method models, and removing one of the methods is called the CTCM-1 model. So to close out this model, another parsimonious model are state trait models. State trait models are one of the models where we talk about in terms of time series or repeated measures or waves of assessment. And here's a picture. So what I have is a behavior that I've measured across 8 times of measurement. And I have arrows that go from one measurement occasion to another. And then I have a trait upstairs. Why do you do this? Well, I've mentioned earlier in the class that very often when people model longitudinal data, they tend to think of time 1 as causing time 2, and maybe time 1 causes time 3. All of the arrows point forward. And this does not make a lot of sense if you're looking at a number of behaviors that appear to be stable inter-individual differences. Now, I know I mentioned this before, but it bears repeating again. Is it the case that we talk about people who have an alcohol problem as saying, oh, well, you have an alcohol problem today because you had one yesterday? We tend to more conveniently talk about alcohol problems as saying that person has a drinking problem. It's a stable inter-individual difference. If you ignore this trait characteristic and point arrows forward, an interesting pattern occurs by means of autoregression, that you'll see a large positive number here and a large positive number here. And if you start saying, well, does time 1 tell us time 3? Well, you'll see negative numbers. And that's not really conceptually interpretable. The reason you get negative numbers is you're multiplying a positive number here and a positive number here. This carries a positive correlation between time 1 and time 3, and we make up the difference if the correlation is substantially lower by estimating a lower number. And I have seen people, try to publish articles that say, there's a good thing, say, when you come to college, to drinking a lot your freshman year, because that means in time 3 you won't. Well, it's the model and the specification issue. There are some students who drink a lot and some who don't. And the way we fit this model is, here's our unstandardized weights and our standardized weights. But upstairs, I've got these traits, these lambdas, and downstairs, I've got these gammas. And we see that the trait, those things, those are very large positive loadings. Downstairs, these effects are relatively small. We do tend to see that there is an effect from time 1 to time 2, it's kind of the freshman year, that is something in addition to this general trait. And downstairs here, the fit statistics for the model and so forth. I mean, this works fine. The only thing that I would say, in terms of fitting these models is we tend in psychology to be in love with them and say, well, this is how things have been published, but you could also fit a random intercept trait component as well. That is, you could say, here's a trait value, all of these loadings are free, and there's a tau equivalent model over here that's orthogonal that has factor loadings of 1, explaining things. And that might even extract more variances and covariances from the model by referencing systematic inter-individual differences. And that's my comment here about right-sizing it. We could estimate a random intercept model and a factor here, and our AR paths make the following changes. So, it's an option. You can certainly do that, and that model will fit, appreciably better and might have different autoregressive paths as a result. Similarly, these 2 latent variables may behave differently as predictors of some criterion, like, say, college graduation, than just having 1 factor alone. All right, that's where we are today. We're at time. I'm going to, as God is my witness, make you a homework at that point. And I'll continue to work up some program examples and start the class off. If you want to bring data that you're working with and questions you have with your analysis, that's fine. We're going to start looking at change and growth. We're going to specifically start looking at longitudinal data now. So this will be the next chapter I'll be lecturing off of. Any questions?